At the end of the last section, 5.2.1, we took a look at the idea that we could use z-scores to help measure certain probabilities in a normal distribution, and that using a z-score calculation would ultimately produce the same result as if I just used the original values given in the problem. You may remember that. I think we did that as a part of example 3 in that section. Now what we're going to see is how that information can actually be used now within this section. So take a look at what I have in the box, because my box here isn't just telling me that, or reminding me what the z-score formula is. It's highlighting something a bit different. The following formula, that is the z-score formula, it relates together 4 different variables. So very interestingly, if I think about this algebraically, if I know the value of any 3 of these, if I could replace 3 of these different symbols with numbers, I could then solve for the remaining value, because I'd have one equation with one mystery unknown, and I could solve for it. Well, we're going to try to use this to our advantage, as well as the idea of z-score probability calculations that we did in the last section. Take a look here at example 3. Suppose that the lifetime of Outlast batteries is normally distributed with a mean of 240 hours. The company is trying to decrease the standard deviation of the lifetime of the batteries so as to improve the reliability of their product. If a product has a lot of variability, it would have a high standard deviation. And you can imagine that's probably not something that a company would want. No company wants to be selling a product where customers don't know what they're getting, right? Can you imagine if you showed up to the store and you bought, I don't know, you bought some batteries, and like one time you buy them, they last you for like 4 years. The next time you buy them, they last for 4 minutes, right? Like you're just not going to go back and buy that product. So having something very reliable is good for sales. So suppose the goal is to make all of the batteries such that only 20% of the batteries end up lasting less than 219 hours, right? They want to be able to guarantee this. They don't want a ton of batteries that are going to last under this amount. They expect a little fluctuation, but they don't want maybe a lot. Look at the interesting question we have here. What should the standard deviation be? Whoa. What should the standard deviation be in order to reach this goal? Notice, that's not a question that's going to involve normal CDF, because it's not a probability question. It's not a question that's actually going to involve inverse normal, because I'm not actually looking for some sort of a value on the number line. I'm looking for a standard deviation. That's wildly different. Well, let's see how we can set up the information that we have. I'm going to start the same way I always do. I'm going to define a variable. So I'll say, how about we let x represent the lifetime of a battery. Okay, one of these Outlast batteries. Okay, we're told x has a normal distribution. And we know that the mean of that distribution is going to be 240 hours, and the standard deviation, well, we don't really know that. So the standard deviation there is really just a question mark, okay? If we can find the standard deviation, we'll be done with the question. Okay, well, do we know anything else? Let's start to see if we can draw a picture here of what's going to be happening. So I'm going to go ahead and sketch out my nice normal distribution. So I'm going to draw my normal curve. Okay, so I know that I have my mean of 240 sitting right here, and my standard deviation of x is, well, still unknown. Well, what is it that I know? Well, I at least know part of the goal, right? I know that there's a goal, and that's to make it so that only 20% of the batteries last less than 219 hours. So this is interesting. I could go ahead and put this number x on the number line, this 219, and I know that if I shade below it, the goal is to have this amount of space be 20%, or 0.20. Okay, so 0.20, that's what I'm looking for. I want this to happen. The question is, again, what do I have to make the standard deviation in order to make that happen? Well, this is kind of tricky. What we're going to see is that if I am going to go ahead and actually think about the associated z-score picture, or the standard normal distribution, I can find something really interesting. Let's take a look at what we have if I was to redraw this picture, but with the standard normal distribution. Remember that the standard normal distribution is going to have a mean of 0 and a standard deviation of 1. That's what it always has. Remember that the variable is now z and not x. But what I'm going to try to do is create a mirror image of what's happening down here. Now, remember that I know that I have 0 because the z-score for 240 is 0, because 240 is 0 jumps away from average. The weird part is, I can't actually calculate the z-score for my 219. The reason for that is that I would need to use this formula to calculate the z-score. And so if 219 goes in place of the x, and the 240 goes in place of the mu, I don't have anything yet to put in place of the sigma, so I can't calculate the z-score directly. However, I know that I can put that z-score still in the same spot in the picture. Let me just call it mystery value z. And remember that what we saw in the last section is that I know that if I go ahead and I find the probability below whatever that z would be, what percentage should be sitting there? Well, it should be the same percentage as what we had up above. Okay, so now we get to bring everything together. Notice, like we saw in the box above, if I know any of these three values, I can solve for the one that's missing. So what if I knew the value of z, and I knew the values of x and mu? If I knew all of those values there, then wouldn't I easily be able to solve for the mystery value of sigma? And notice I already have x as 219, I already have my mean as 240, if I could only find this z value. The problem again though is that I can't find the z value using this formula, but I think there's another way that I could find the z value. I'll say we see that z is just a number on my number line. So I could find it using inverse norm. I would just put in the area to the left of the z, and then the mean and the standard deviation from that picture, because z's on this picture, it's not on this one. But notice, this then is something I can immediately compute. That's fantastic. In fact, if you were to go ahead and type this into the calculator, and following the instructions in the problem that says round everything to 2 places, you would get a value of negative 0.84. Now remember, it's totally okay for this to be negative because it is below 0, so it should be a negative number down there. But now I can see that we have the following. We have a value of x, z, and our value of mu. So we can fill in our formula of z equals x minus mu over sigma and solve for sigma. Right? We have 3 of the values. So let's go ahead and just start filling it in. Okay, so I have negative 0.084. That goes in place of the z. On the top of the fraction, I'm going to have my 219 and then minus my 240, and that's over the sigma. Okay, so let's take this slow and deal with this one step at a time. All right, so going down here, I'm going to have negative 0.84. And let's see, if I do 219 minus 240, that's going to get me a negative number on the top of that fraction. That's going to get me something like, I think, negative 21, and I'll still be over sigma. If I want to solve for sigma, I can multiply it to the other side. Let's move over here. So this would be negative 0.84 times sigma equals negative 21. Now I could just go ahead and say to solve for sigma, I would just take my negative 21 and divide it by my negative 0.84. Notice this is good because I should have my sigma as a positive number. Sigma is always going to be positive. So the fact that I have 2 negative numbers here is great news. You can even double check though. If you go and you crunch this out in the calculator, you actually come out with a nice value of 25 hours. And so we have answered our question. What should the standard deviation be to guarantee this sort of batteries, or batteries behaving in this way? We need to have the standard deviation be 25 hours. Here's where you can start to see again all of the different features that we've started to talk about in this class kind of coming together. We can see how we are using means and standard deviations in different distributions. We're using the ideas of z-scores, what we talked about in the last section, to help find mystery values. Notice that we could do the exact same thing if, say, I told you any of these three values. In this one, the standard deviation was unknown. But what if I gave you one where the mean was unknown? Well, you could do the same exact thing. If I gave you instead something like an x or a z that was unknown, that would be even easier to work with because you wouldn't probably have to work as hard with these distributions. But of course, go ahead, take a look at the worksheet questions that we have, and you'll be able to see a variety of different examples where we can try to work through problems like this one. Of course, if you have any questions, please feel free to let me know.